grade 12s. Welcome to our STEM in Action Grade 12 Boost series. And today we are going to be looking at the topic rates and extent of reactions. So to begin with, we are going to look at some of the pre-knowledge that you are supposed to know from your grade 11 and grade 12 that applies for this topic. And some of the pre-knowledge that you need to know. The first thing is you need to know how to calculate percentage yield. So the formula for calculating percentage yield says the actual yield divided by the theoretical yield times 100. So this is a formula that by now you should be already familiar with. And the next formula you should be familiar with is the one for calculating percentage purity. And it says that percentage purity is equal to the mass of the pure substance divided by the mass of the impure substance times 100. So I'm going to assume that you know already how to calculate percentage yield and percentage purity. And something else that you are also going to need to know about, which you also learned already in grade 11, are enthalpy graphs. So this is an enthalpy graph. And what you notice is that an enthalpy graph is showing us here on the y-axis the potential energy and on the x-axis the reaction time. And it's basically showing the progression in energy levels of our reactants as we move from reactants to products. So notice that we are starting with our reactants on the left-hand side, and they have to climb up, you can say, they have to climb up an energy barrier called activation energy, and only then do they come out on the other end to form products. And the energy difference between our reactants and our products is what we call the enthalpy energy. And we are going to look at this graph in more detail as we progress. So for introductions, reactions proceed at different rates depending on the conditions and also on the type of reaction. So here you can see this is an image of a rusting school bus. And that's an image of a reaction happening, which can happen in a lab, the reaction between a magnesium ribbon and hydrochloric acid. And this is a reaction, a chemical reaction of fireworks. And basically fireworks are simply explosions, almost similar to, they have the same chemical properties that are found in gunpowder. So when you are shooting a gun, you're actually creating an explosion which sends the bullets away. And you have got the same type of reaction happening when you are having a chemical explosion. All these three are chemical reactions. So in a rusting of a bus, you are basically reacting iron with oxygen in the presence of water. And for the second one, I already talked about it. But what you notice is that between these three reactions, they occur at very different rates. So the first one might take years to happen. And the second one can happen in a few minutes in a lab, and an explosion can be over in a second. And the difference between the time periods it takes is simply the nature of the reactions. And I would also like to highlight the fact that we can speed up each of these reactions. So the rusting of metals, we can speed it up if you provide an acidic environment, or we can slow down the second reaction by changing the conditions of a reaction. So we are going to look at various ways in which reaction rates differ, and also the various ways we can improve on the rate of a chemical reaction. So rate of a reaction, a chemical reaction involves changing reactants into products. So when you are doing a chemical reaction, you are basically starting with some reactants, and you are doing a chemical reaction, and you are converting them to products. So this is an example of a chemical reaction where we are reacting calcium carbonate with hydrochloric acid, and we form calcium chloride plus water and carbon dioxide. It's a neutralization reaction. And what you notice there is that these are our reactants, calcium carbonate and hydrochloric acid, and these are our products. And when we want to define the rate at which this reaction happens, we can define it in two ways. So the first one, we can consider the rate at which our products are being formed. So on the right-hand side, we have our products, and by measuring the rate at which our products are being formed, we can get an idea of how fast the reaction is happening. And to do that, we simply need to identify one of the products whose accumulation over the progress of the reaction we can measure. So if we can find an instrument, so when we are trying to measure the rate of a reaction, we use various instruments. So if we can find an instrument that can allow us to measure the rate at which calcium chloride is accumulating, or the rate at which water is accumulating, or carbon dioxide is accumulating, we can use that rate to determine the average rate of the full reaction, right? Another way we can measure the rate of reaction is by using the reactants. So we can use this formula which says that reaction rate is equal to the amount of reactants used over time. So as the reaction progresses, we are going to be using up our reactants, and we can use the rate at which those reactants are getting used up to decide on the rate of the reaction. And we can come up with a graph such as this one. So if we look at this graph, we have got the amount of reactants or products on the y-axis, and we have got time on the x-axis. And we have two graphs which are showing us, firstly, we have got the graph showing us the accumulation of the product, and we've got another graph showing us the depletion or using up of our reactants. So if we look at this graph, we'll notice that at time 0, we do not have any products because the reaction has not yet started. But our reactants are at their maximum. And as our time progresses, our products are forming, and therefore the amount of our products is increasing, as our graph is showing, and to a point whereby time is still moving, but the amount of our products is no longer changing. And at that point, we can say that the reaction has been terminated, or the reaction comes to a stop. And we can also look at the same on our reactants graph, and you'll notice that as the reaction progresses, the amount of our reactants is decreasing as they get used up in the reaction, until a point where our graph flattens, and at that point the reaction is terminating and the reaction stops. And if you look at this graph also, we'll notice that we can talk about the gradient of the graph, right? And so the gradient of the graph is going to be change in the y-axis over change in the x-axis, which is simply change in the amount of products over time, which is our x-axis. So if we talk about our product graph, you notice that our gradient is changing as time progresses. So at the beginning of our reaction, we have got a very steep graph, which indicates that the rate of the reaction is very fast at the beginning of the reaction. But as the reaction progresses, our graph is becoming less and less steep until the gradient of the graph becomes 0, at which point the rate of the reaction is now 0, or the reaction is no longer happening. And the same can also be observed with the reactant graph, that the gradient of the graph starts very steep, and it gets less and less steep as the reaction progresses, until such a time as when the gradient is now 0 and the reaction stops. So using such a graph, we can determine the amount of product or reactants at any given time. So next, we are going to look at a typical exam question that you get, or a typical graph that you have to analyze. So part of this topic is being able to look at a graph, interpret what the graph is saying, because a graph tells you a story, and you have to be able to be able to interpret the story that the graph is telling you. So here we have got a graph, and what this graph is telling us, we are measuring the volume of a gas that is being produced over time. So what you notice is that it can be a typical reaction whereby the reaction is a product that is a gas. So by measuring the amount of gas being produced, we can get a volume of the gas being produced over time. So starting at 0 before the reaction starts, and once time starts moving and the reaction starts happening, we are accumulating our gas, and the amount of gas is increasing, right? Until such a time, so if you look at our graph, you notice that at around time 12 seconds, our graph is now flat, and we can identify 12 seconds as the time at which the reaction stopped. But it is possible to try to find the average rate between 2 points in a graph. So in this case, we are going to try to find the average rate of the reaction between time A and time B. So to find the average rate of the reaction between point A and point B, we are going to apply our formula, and we are going to say that the reaction rate is equal to the volume of gas formed over the reaction time. And so volume of gas formed is going to simply be the final gas minus the initial gas. So the volume of gas formed is going to be the final volume at point B minus the initial volume at point A over the time at point B minus the time at point A. And if you look at that, you notice that our volume at point B is around 8.7 cubic centimeters, which is our final volume, and our initial volume at point A is about 7.5 cubic centimeters. And our time here, our final time is about 10 seconds, and our initial time there is about 6 seconds. And from here, it is simply pure maths. It's a mathematical calculation. And if you put that in a calculator, you're going to get 0.3 cubic centimeters per second. And these are our units because we are dividing our y, which are cubic centimeters, over our x, which is seconds. So if you look at this graph in general, you also notice that the gradient of our graph is starting very steep, and it is getting less and less steep, indicating the slowing down of the reaction as time progresses, until the point where our graph flattens. So at the point where your graph flattens, which here is around 12 seconds or 14 seconds, that is the point or the time where the reaction stops. And you also notice that if we can draw a second graph, which is going to be this one, and this is the graph that we would get for a slower reaction. And what you notice there is that this graph is less steep, or the gradient of this graph is less steep than this, the gradient of the first graph. And at the same time, it also takes more time to reach completion. So if we are identifying this part where the volume of our gas produced is going to be the maximum of the volume of our gas produced is going to be 9 cubic centimeters, you will notice that our second graph takes longer to get to that volume. So this is what the graph of a slower reaction is going to look like. And this is the graph of what a faster reaction than our original reaction is going to look like. And you notice here that the gradient of this graph is way more steeper than our original graph, and it takes less time to reach the maximum volume of gas produced. And even just by looking at them, if we just consider this line here, we'll notice that at this time, the slower reaction has only produced about 5 cubic centimeters of gas, but at the same time, our original graph has produced about 7.5 volume of gas, yet the faster graph would have produced at this point more than 8 cubic centimeters. So those are the three graphs that you can expect to produce, whereby this is the fastest reaction, the average reaction, and this will be the slower reaction. Next, we are going to look at some of the methods or tools that are used to measure the rate of a reaction. And in deciding which method to use or which tool to use, you have to consider the reaction. So different type of reactions allow for different methods to be used to measure their rate. And in most of your questions, they will identify one of these methods as an examination point. So be familiar with each of these four methods, and when you see a graph or an image come up, immediately know what method you are using, and already you should have an idea of what to look out for in answering the questions. So the first method is one where we are measuring the volume of gas produced per unit time. So as you can see, if we are measuring the volume of gas produced, it means that the reaction should be producing a gas. So I'm going to come back to our initial reaction example, which is a reaction between calcium carbonate and hydrochloric acid. And what you notice there is that in our products, we have got a gas. So we can use the production of this gas to determine the rate of this reaction. So as the reaction progresses, this gas is going to be produced as part of the product, and we can have a setup or an experimental setup such as this one. So if you look at this experimental setup, we have got our reaction flask, and we connect our reaction flask to a syringe. And this part here has to be airtight so that all the gas that is produced in the reaction only goes up into the syringe. And when the reaction begins, we are going to be having our reaction mixture here. So it means that we'll be having our calcium carbonate, which is a solid, and we are going to be having our hydrochloric acid, which is an aqueous liquid. And when the reaction starts, before the reaction starts, there will not be any gas produced. So our syringe is going to be right here at Mach 0. And once the reaction starts, the gas being produced, which is our carbon dioxide, is going to accumulate on top of the reaction because it's a gas, and it's going to move up the syringe, and it will begin to push the syringe to the right, and we can begin to record the volume of gas produced. So over time, obviously, we have to do this reaction with a stopwatch so that we can measure the time, and we'll get a graph such as this one. So what you notice, like I've said, at time 0, there is no product yet, so the volume of gas produced yet at that point is going to be 0. And as the reaction, once the reaction starts, we are going to start producing gas, and as the gas gets into the syringe and starts accumulating in the syringe, the volume measured here is going to start increasing. So what we get on our graph is basically indicating an increase in volume as time progresses, until that point whereby time is still moving, but the volume of gas produced is no longer changing. So once the graph flattens, it means that the reaction has stopped. And we also notice here, like we have indicated, that the gradient of the graph is starting very steep and is slowing down as the reaction progresses until it flattens. And I'm going to look at why that happens later on. And the next method that you are going to look at is measuring the change in mass per unit time. So we are going to come back to our original equation, and we have already talked about this equation, and I'm going to display here the setup of the reaction. So in this setup, you notice that our setup looks almost the same as the one we had for the previous example, but the difference now is that we are not collecting our gas. So our setup here, we have got a mass balance, which is going to be measuring the mass of our reaction system, and that includes our reactants, our reaction container, which is our flask, and everything in it. And also, so here we have got our reaction mixture, which is our calcium carbonate and our hydrochloric acid, and here we've got a cotton wool. And the use of the cotton wool is simply to prevent any material from leaving the flask except gas. So cotton wool is a porous material, and in this case, it prevents any other material in any other state, such as solid or a liquid, from going out of the reaction flask, but it allows gas to escape. So in this setup, we also notice that one of our products is a gas. And in fact, that is the only gas that is part of this reaction. As a result, as the gas is being produced, it is going to escape through the cotton wool. And obviously, gas has some mass. It is light, but it still has some mass. So as the reaction progresses, as the gas escapes through the cotton wool, it means that our reaction system is going to be losing mass. And we can use the rate at which that loss in mass happens to decide on the rate of the reaction. And we'll get a graph such as this one. And what you notice there is that at our time 0, so this is a graph where our y-axis is the mass of the flask contents. So, and our x-axis is time. So on the y-axis, we are measuring everything that is here, right? The reaction flask and the contents of the reaction flask. So starting from time 0, you notice that the mass of our reaction system is going to be decreasing until around this time where our graph becomes flat, which indicates that the reaction has stopped, or the mass of the system is no longer changing, Therefore, we are no longer losing gas, which means that the reaction is no longer producing a gas product. So you can take the point where the graph flattens as the point where the reaction stops. And I also want to indicate here that our graph is not going to go down to zero, simply because we still have our material. So you might think that you expect the graph to go down to zero like the other graphs we have seen before. But if you look at this graph and you try to think about it, we are measuring the mass of our reaction system, and you're only losing the gas, which is a product, but we still have everything remaining on the mass balance. So our mass is not going to get down to zero. But the thing to note is that one of our products is an escaping gas, and we can use the change in mass to measure the rate of the reaction. So our third method is called measuring change in turbidity per unit time. So there are some reactions whereby when you start the reaction, you start with a clear solution. And as the reaction progresses, your solution becomes less clear. And turbidity is simply a measure of how clear a solution is. So we say that a solution is turbid when it is not clear or cloudy. So if you look at this reaction, it's a reaction between sodium thiosulfate and hydrochloric acid, and we produce sulfur, sodium chloride, sulfur dioxide, and water. And what you notice is that one of our products is a solid, and it is the only product that is a solid of our products. And as a result, when we start this reaction, we start with a clear solution with only sodium thiosulfate and hydrochloric acid. But as the reaction progresses, as we produce sulfur, the sulfur will cause the solution or the reaction mixture to become cloudy because it's a solid. And that cloudiness is what we call turbidity. So we can use the rate at which our solution turns turbid or turns cloudy to decide the rate of the reaction. And to do that, we will simply have a paper and we draw an X, and then we put our reaction mix on top of the paper or our X. And when we start, our X will be visible, like we can see here. But at the end of the reaction, our X will have disappeared, or it becomes obscured or covered by the cloud or solution. And if you look at this table, it's basically showing different conditions of concentration between, so we've got experiment 1, 2, 3, and 4, and 5, whereby we're decreasing the concentration of sodium thiosulfate. And what you notice is that the time it takes for the X to disappear is also increasing, meaning to say that the rate of the reaction is becoming slower and slower as we decrease concentration. So you can be familiar with such a table and how to interpret what the table is saying, and this image, which is basically a measure of deciding the rate of reaction based on the change in turbidity. I'm going to do a simple experiment to demonstrate this, and then we'll just move on to the next method. So we are going to do our turbidity experiment, and what we have here is our sodium thiosulfate as 0.1 molar sodium thiosulfate and 1.0 molar hydrochloric acid. And this is going to be our reaction setup. I'm going to use here 50 cubic centimeters of sodium thiosulfate, and I'm going to pour it both into our experiment and our control. So that's 50 cubic centimeters of sodium thiosulfate into one beaker. And 50 cubic centimeters into the other beaker. And you can see that both beakers are clear. We are able to see our X from the top of the beaker. Now I'm going to add our hydrochloric acid, but I'm only going to add it to this beaker, and I'm going to keep this beaker as our control. And I'm also going to add the same volume. Uh, 50 cubic centimeters, and I'm only adding it to one beaker, and our expectation is that the beaker into which we are going to add our hydrochloric acid is going to become turbid. So I'm going to add now, and we are keeping this one as our control. And we are going to simply watch from above and see what happens to the X from both beakers. As you can see, this beaker is beginning to become turbid. So one of the products that we are forming is our sulfur, which is a solid, and it's going to be a solid precipitate. And it is the reason why this reaction mix is becoming turbid. And we can see that our control beaker is remaining clear, and our X is disappearing slowly. And now it has completely disappeared. So the rate at which that X disappears is going to give us an idea as to the rate at which the reaction is happening. So the fourth method, which is the last one, is measuring change in color per unit time. So there are some reactions that result in change in color, and we can use the rate at which that change in color happens as a reflection of the rate of the reaction. So you get a reaction such as this one, and for this reaction, we are reacting sodium hydroxide with iodine, and iodine is a brown aqueous solution, or is a brown liquid. And as this reaction happens, we are using up our iodine, and therefore our solution or reaction mixture is going to become less and less colored. So you get a result which looks like that, where we start off with a very brown reaction mixture, but as our iodine gets depleted or used up, our solution becomes clear and clearer. And if we are measuring the rate at which that color change is happening over time, we'll get an idea of the rate of that reaction. And next, I'm just going to display all the four methods that we have looked at. So we looked at measuring change in the volume of gas produced, measuring change in mass per unit time, measuring change in turbidity per unit time, or measuring the change in color per unit time. Next, I'm going to look at the collision theory. So the collision theory looks at the dynamics of the rate of reaction. It looks at, you are zooming in into what is actually happening with the reactants at atomic level, and you are deciding how we can influence reactions to be faster or slower based on the reaction dynamics. So for a reaction to happen successfully, there are three things that have to be met, or three factors that have to be met. And when a reaction happens successfully, we say that we have an effective reaction or collision. So the first thing that has to happen is that the reactant particles have to collide. And obviously, you cannot have reactants reacting if they are not coming into contact with each other. So the first thing, they have to collide. And obviously, for them to collide, they have to be moving. So the second factor, so if you look at this image, we are reacting here carbon monoxide and oxygen. And for a reaction for this to react to form carbon dioxide with a byproduct of an oxygen atom, they have to collide. And when they collide, they must have enough energy. And this is just represented here by this image here. And with enough energy, we know that when a reaction is happening, there are things that happen, such as breaking of bonds and forming of bonds, and those processes involve energy. So when they collide, they must have enough kinetic energy for them to react. Then thirdly, they must be of the right orientation. So you notice that this applies mostly, for example, with large molecules. So if you've got a large molecule, maybe it's only a part of that molecule that is actually participating in the reaction. And if the reactant bumps onto the wrong part of the reactant, then there's no reaction that is going to happen. It has to bump on the right side or right part of the molecule for the reaction to happen. So if you look at this, we are still reacting carbon monoxide with oxygen, but you notice that for this reaction to happen, the oxygen has to collide with the carbon. If it collides in the other way around, whereby the colliding atoms are oxygen, oxygen, then there's not going to be a reaction. So the right orientation has to be met. Now, we are going to look at some of the factors that affect the rate of reaction. And these factors, they are related to the three aspects that we have looked at. So when you are addressing factors that affect the rate of reaction, you have to address them in relationship to the three factors that we have looked at already. So the first one is the nature of the reactants. So this is talking about things such as the state of matter of the reactants. And in most cases, generally, gases react faster than liquids, and liquids react faster than solid. And also with the nature of reactants, we're also talking about the size of the reactants. The smaller the reactants are, usually the faster the reaction happens. If they are larger molecules, it takes longer for them to bump into each other or collide in the right orientation and stuff like that. The next one is temperature. And generally, we know that as you increase temperature, you increase the kinetic energy of your reactant particles. And the higher the temperature, or the higher the average temperature, the higher the average kinetic energy of each individual particle. And the higher the kinetic energy, the faster the particles are moving around, which increases their chances of colliding, which also increases the chances of effective collisions. Then the third one is concentration, and concentration is simply a measure of the amount of reactant particles per unit volume. So the more reactant particles we have per unit volume, the higher the chances of them bumping into each other, which improve the chances of effective collisions. So we're going to do a fate simulation to illustrate the effect of concentration on the rate of reaction. But most importantly, we are trying to illustrate the fact that when we have got a low concentration, this is going to be our situation where we've got a low concentration, we have fewer reactant particles, versus a situation where we have a higher concentration or of more reactant particles per same volume, right? And we said that for a reaction to happen, the reactant particles must collide. So if we start with the lower concentration one and we press play, you notice that the rate at which we are getting collisions is very low. So the frequency of collisions is very low. So the chances of successful collisions is going to be very low. But if we play the one where we have a higher concentration and more reactant particles, we'll notice that there is a higher frequency of collisions, which increases the chances for a successful collisions. So as you increase your concentration, you increase the rate at which your particles are colliding into each other, which increases the chances for successful collisions that result in a product. Also here you'll notice that I can change my temperature. And here I'm starting with my temperature quite high. And what you notice is that there is this image, and I also want you to be looking at that graph, which shows the average or the total average energy of our reactant particles. And we are familiar with this graph already, and we know that this is our activation energy. And only when our average energy for our particles is more than the activation energy can a reaction proceed. So I'm going to click play, and I'm going to start with a low temperature. And our total average energy is going down. And you notice that at a lower temperature, the kinetic energy of our particles is going to be low. And because they'll be moving around less, or they are moving at a less rate, the frequency of their collision is going to be low. And therefore, you have less chances of successful collisions. But once we increase our temperature, we are going to increase the kinetic energy of the particles. They will start moving around faster, and the chances of them colliding into each other is going to increase. And therefore, as you increase temperature, you are going to be increasing the number of effective collisions. And once the amount of energy in the particles, the average energy is more than our activation energy, we are going to start getting products from our reaction. And then fourthly, pressure. So pressure is almost concentration of gases, right? So the higher the pressure of gases, the more concentrated the gas particles are. And fifthly is surface area, and surface area applies for solids. And the greater the surface area, the faster the reaction happens. So increase in surface area promotes the rate of a reaction. And when you are increasing the surface area of a solid, we simply need to crush it into smaller and smaller pieces, and that will increase the surface area. And I'm just going to illustrate this concept briefly. If you move from a large mass of a sample and you cut it in smaller pieces, you're going to be increasing the surface area. So if you look at this and we say that this is our reactant, you notice that these three pieces are around the same size. But this one is one large piece, but this one we cut it into two and we have two more pieces from it. And this one we have cut it into 4 pieces. And we are going to count the surface area of these 3 different experiments set up, right? Whereby as we go from left to right, we are increasing the surface area, and I'm going to illustrate that. So if we take this one and we count our surface areas, we have got 1, 2, 3, 4, 5, 6. So this one has 6 exposed surface areas. Then you come to this one, it has 1, 2, 3, 4, 5, and 6, but there are 2 of them, so we'll say 6 times 2. Then you come to this one, which is going to be 12. We come to this one, we have 1, 2, 3, 4, 5, and 6 again, but we have 4 of them, so we have 6 times 4, which makes the total surface area to be 24. So as we move from one solid mass, as we crush it into smaller and smaller pieces, you are increasing the surface area. Then the 6th factor is a catalyst. So a catalyst is a substance that we add to a reaction to speed up the rate of a chemical reaction, but the catalyst itself is not changed by the reaction or does not participate in the actual reaction except to speed up the chemical reaction. So what are some of the mechanisms of a chemical reaction? We're going to start with the definition, activation energy. So activation energy is simply the minimum amount of energy required for a reaction to proceed. So when particles collide, they must have a minimum amount of kinetic energy for them to be able to produce a product from their collision. And that energy is called the activation energy. And there's a graph which illustrates that. So if you look at this graph, I'm going to show the other graphs. The 2 graphs are showing us the same concept, but they are different graphs, and we're going to illustrate what their difference is. So here we have got our reactants. They start at this energy level, and every reactant must have enough energy, more than the activation energy, for it to be able to be converted to product. And you will notice that also the energy difference between our reactants and our product is what we call the enthalpy energy. And for this graph, our reactants have lower energy than our product, which means that this reaction is absorbing energy from the environment. Therefore, it is an endothermic reaction, and we end up with products with higher energy. And our enthalpy energy sign is going to be positive because energy is flowing into the reaction system. And this is a similar reaction, except that our products have less energy level than our reactants, and that's an exothermic reaction. But we also have the same situation that our reactants must have enough energy, more than the kinetic energy, before they can progress to form products. And you have to know how to draw this graph. You have to practice drawing the graph and also be able to label this graph. Then we have got a graph which is called the Maxwell-Boson curve. And what it basically shows is that if we have got our reactant particles in a system, what is the average energy of each particle? So if you look at this graph, it's showing on the y-axis the probability of particles having that kinetic energy, and on the x-axis it's showing us the kinetic energy of particles. So what does it represent? It's showing us, for example, that if we say that our kinetic energy is increasing as we go to the right, it's showing us that the amount of particles or the probability of particles having low kinetic energy is very small. And as we increase our kinetic energy to an average kinetic energy, there is a higher probability of having particles with an average kinetic energy. But as we get to higher and higher kinetic energy, the probability of particles in our reaction mixture having higher kinetic energy will start decreasing. And at this point, this is our activation energy mark, and only particles that have more energy than this mark are going to be having sufficient energy to be able to react and form a product. And that's a graph you also have to be familiar with, and we are going to show what happens when we increase temperature. So when we increase temperature in a reaction, your Maxwell-Boson curve is going to shift to the right. So here we have got the two graphs represented, one showing one for lower temperature and then another one for higher temperature, which has shifted to the right. And what you notice is that when we shift our graph to the right, we now have more particles having sufficient energy or energy higher than the activation energy. Therefore, by increasing temperature, you increase the number of particles with enough energy to be able to react. The next graph we're going to look at is portraying the effect of a catalyst. So we are already familiar with this graph, and what you'll observe is that for an uncatalyzed reaction, the activation energy will start from there, has to be from this point up to that point. But once we add the catalyst, the activation energy required is going to be lower from that point to that point. So a catalyst provides the reaction with an alternative reaction path or a route which requires lower kinetic energy. And as a result, more and more particles will be having sufficient energy to react. And I would like also to observe that a catalyst does not change the enthalpy. So we are still ending up at the same energy level as the one which is uncatalyzed. And we can also show the same thing using a Maxwell-Boson curve. And what you notice is that when we have got a reaction that does not have a catalyst, our activation energy mark is going to be there. But once we add the catalyst, the mark is going to be shifted to the left to a lower kinetic energy, such that more particles are going to be having sufficient energy or energy more than the activation energy. And that's how a catalyst will speed up the rate of a chemical reaction. Next, we're going to look at some applications. Our application question is going to come from the November 2016 paper, question 5. So if you look at this question, it's saying that we have hydrogen peroxide decomposes to produce water and oxygen according to the balanced equation, and we're given the balanced equation. Then it says that the activation energy EA for this reaction is 75, and the heat of reaction is minus 196 kilojoules. The first question says define the term activation energy. So we have already defined this term, and we said that it is the minimum energy that reactants must have at the moment of collision for a reaction to take place. Then question 5.1.2 says redraw the set of axes below in your answer book and then complete the potential energy diagram for this reaction. So we're simply going to redraw these axes that are already given on the question. We'll start with our y-axis. And on our x-axis, we have costs of reaction. And on our y-axis, we have potential energy and the units. And we have got our zero mark here. Our hydrogen peroxide, this is the zero mark. So looking back at our question, it says that the activation energy is 75 kilojoules. And we know that our activation energy starts from our reactant going up. So we are simply going to go up. And at the point where our graph turns, that is where our activation energy is. And that point is going to be where our 75 is. Then it says that our enthalpy energy is negative 195. So we know that our enthalpy is the change or the difference between our starting energy level for our reactants and our ending or our energy level for our products. In this case, it is negative. It means that it's going to be less than our energy for our reactants. And it's negative 196. So we're looking at a graph that looks something like that. And this is where our product is going to be. And the mark here is negative 196. And it says indicate the value of the potential energy of the following on the y-axis, the activated complex. So our activated complex is always going to be right at the summit of our curve here. So this is where our activated complex is going to be. And also our products, they are going to be here at the end of our energy graph. And this energy difference between our starting reactants and our ending product is our enthalpy for the reaction. Then, coming to the next part, it says when powdered magnesium dioxide is added to the reaction mixture, the rate of the reaction increases. On the graph, for question 5.1.2, which is this graph, use broken lines to show the path of the reaction where the magnesium dioxide is added. So magnesium dioxide here is acting as a catalyst, and we know that a catalyst acts by providing an alternative route for the reaction which has lower activation energy. So we are going to get a graph which starts from here, but does not go high up to the uncatalyzed reaction in terms of, and then it comes there. So this is going to be the activation energy for our uncatalyzed reaction from our starting point to that point, as opposed to that one, which is the activation energy for the uncatalyzed reaction. So this is a graph for the catalyzed reaction. Then it says use the collision theory to explain how magnesium dioxide influences the rate of decomposition of hydrogen peroxide. So we said that a catalyst provides an alternative route that has a lower activation energy, meaning to say that more reactant particles will have sufficient energy to be able to react effectively. So firstly, a catalyst provides alternative reaction pathway with lower activation energy, and more particles will now have sufficient energy more than the activation energy. And as a result, you are going to have more effective collisions, and because of that, the rate of the reaction is going to be increased. Our next question is question 5.2. And here we've got a graph. We have two graphs, graph A and B, and they are obtained for the volume of oxygen produced over time under different reaction conditions. So these are graphs for our reaction, and they're measuring the volume of oxygen produced. 5.2.1 says calculate the average rate of the reaction in decimeter cube per second between time 10 seconds and time 40 seconds for graph A. So this is the graph that you are interested in, and the time, our initial time is going to be 10 seconds, and you'll notice that the scale of our graph on the x-axis is a scale of 2 seconds. So if we count from here, we're going to say 2, 4, 6, 8, 10. So this is where our 10 seconds is. So we are going to draw a vertical line from our time of 10 seconds here. uh, to intersect our graph A and then draw a horizontal line to intersect our y-axis. And the volume that we have here is 16 decimeter cube. And our time for 40 seconds the volume that we have here is about 52 decimeter cube. And to calculate our average rate, we are going to say average rate is equal to change in volume which is our y-axis over change in time. And our change in volume is 52 minus 16. And our time is from 40 seconds minus 10 seconds. And we are going to get an answer of 1.2 decimeter cube per second as our final answer. Moving on. So question 5.2.2 says, use the information in graph A to calculate the mass of hydrogen peroxide used in the reaction. And assume all the hydrogen peroxide decomposed. And says use 24 decimeter cube per mole as the molar volume for oxygen. So we write our equation, and our equation says 2 hydrogen peroxide H2O plus oxygen. And we are told that if we look at our graph, we'll notice that at the end of the reaction, we had produced 60 decimeter cube volume of oxygen. So it's 60. And we have to convert that to moles before we can apply the stoichiometric ratios. So to do that, our formula says moles is equal to volume over molar volume. And our volume is 60. And our molar volume is given as 24. And if we do that, we are going to get 2.5 as our number of moles. Then we come back to our equation, and we are saying here we have got 2.5 moles of oxygen. And if we apply our stoichiometric ratio, we realize that this is 1:2 and we are trying to calculate the mass of hydrogen peroxide. Therefore, the ratio between our moles of oxygen and hydrogen peroxide is 1:2. Meaning to say that we have to take that 2 moles and multiply it by 2 to find the moles of hydrogen peroxide. So here is going to be 2 times 2.5, which is going to give us 5 moles. So now that you have the moles of hydrogen peroxide, we have to convert those moles into mass. So our formula for doing that says that mass is equal to moles times molar mass. And our moles is 5 moles. And our molar mass for hydrogen peroxide, we have got the mass for hydrogen is 1, but we have 2 hydrogens, plus the mass for oxygen. Molar mass for oxygen is 16, but we have 2 of those. So we're going to get 5 times, this is going to give us 2 plus 32. Therefore, 5 times 34, and we are going to get 170 grams. So the mass of hydrogen peroxide is going to be 170 grams. So 5.2.3 says that how does the mass of hydrogen peroxide used to obtain graph B compare to the mass used to obtain graph A? So if you look at our 2 graphs, you'll notice that they are producing the same amount of oxygen. Therefore, it means that they are using, or the amount of hydrogen peroxide used for both the reactions is the same, except that one is faster than the other. Therefore, the mass is going to be equal. Then our last question, which is 5.3, says 3 energy distribution curves for the oxygen gas produced under different conditions are shown below. The curve with the solid line represents 1 mole of oxygen gas at 90 degrees Celsius. So the solid line represents 1 mole, so this is important, and our temperature is important. Then it says choose the curve P or Q that best represents each of the following. 1 mole of oxygen gas produced at 120 degrees Celsius. So we said that when we increase the temperature, our curve is going to shift to the right. So we're looking for the curve that is shifted to the right, and that curve is going to be Q. So for 5.3.1, our curve is going to be curve Q. And then 5.3.2, it says choose the curve that best represents 2 moles of oxygen produced at 90. So our temperature is the same, except that we are now using, or we are now producing 2 moles of oxygen. Therefore, you are going to have a bigger graph with double the volume, and that graph is going to be graph P. So our answer here is going to be P. And this marks the end of our application questions.